Hi everyone, welcome to this course in quantum many-body theory in condensed matter physics, given here at the Institute of Physics at the University of Sao Paulo. My name is Luis Dias da Silva, and I'll be teaching this course. So let me start by just presenting the web page where we're going to upload all the materials, which is going to be on the Moodle platform at USP. Let's see if I can change. So here it is. This page is in Portuguese, and it is open to to the outside world, so to speak. But you have to be enrolled in the course to submit your projects and your assignments. But other than that, you can come here and download the PDFs for the classes and everything. So it's going to be pretty much open, except if we need to be enrolled in the course in order to upload the material. Okay. So also all the lectures will be posted in my YouTube channel. Here's the link. And this is the first video in this series, in this playlist, where I'm going to present the course. So let's just dive in and take a look at what's coming. Okay, so let's go over the course contents here. We're going to start by introducing the second quantization formalism. We're going also to review quantum mechanics a little bit, and then dive right into second quantization, talk about representations in quantum mechanics, Schrödinger's representation, Heisenberg representation, interaction representation, things like that. I'm going to talk, of course, about field operators coming out of the second quantization formalism, then move on to time-ordered Green's functions, both at zero temperature and at non-zero temperature. We're going to talk about Matsuburg frequencies and all that, and then how to use Feynman diagrams and Wick's theorem in order to calculate Green's functions for interacting systems, correlation functions, things like that. Let me just say that if you have seen these formalisms in a quantum field theory course, usually which is targeted towards high energy physics, and then there you probably have seen like field operators in a relativistic covariant form. We're going to treat them in a slightly different way. Essentially, our focus is going to be physical systems in condensed matter. So it's good that if you already come with this background, it's fine. You're just going to see it in a different light. If you have never seen this, it's also fine. We're going to cover from the beginning, right? And then we're going to apply that to physical systems in condensed matter. Especially, and this is like the workhorse for the course, which is the electron gas. I would say it's almost like the hydrogen atom in condensed matter. The electron gas. We start with the non-interacting electron gas and solid state physics courses, and here you're gonna treat, at least at the level of perturbation theory for sure, using the RPA formalism, what changes if you include electron and electron interactions in the electron gas. And also we're going to talk about mean field theories. Hartree-Fock is an example. We might do others. And this is important as it gives you many insights into models such as the Hubbard model, which to a first approximation you get some insight by just a mean field treatment. We're going to also see other important models using this formalism, such as the Anderson model, the Condon model, the Heisenberg model, spin models in general, you can put in here, and how you calculate, again, correlation functions and things which might be important. For instance, we're going to do a whole class on the Anderson model and the Condon effect and talk about transport in mesoscopic physics. And transport quantities are, in a sense, calculated through a correlation function, or from a Green's functions, if you want, a retarded Green's functions. We're going to see that and see how you can use these formulas to calculate things that you can actually measure in the experiments. And that's a very, very important part of the course, is to try to make a connection with the experimental results, both the classical experimental results for the electron gas, but also in superconductivity is another example where there's many, it's a very well understood phenomenon in at least in metals, where BCI theory makes a good job in describing them, that we're going to go over that. And then this is one very good example where the theory essentially matches the experiments pretty much. And at the end of the course, we're going to cover some new topics such as topological insulators and topological superconductors, Majorana bound states, and condensed matter physics, which is our current research topics. We're going to do a few lectures on those, and that's how we're going to finish the course. So pretty much this is the content. In a moment I'll tell you how the sequence will be, but let me just say here, and this is interesting. Overall, this has a motivation which comes from what some people call emergent phenomenon in physics, and is very present in condensed matter systems, especially strong correlated ones. And that's sometimes referred to as the Morse different paradigm, by a very famous paper by Phil Anderson in the 70s. And then there's a more recent paper by Bob Laughlin and Robert and Pines. And there, David Pines. And we're actually going to go over these two papers in this video. And this is related to the first assignment, very first assignment of the course. And more is different, and we're going to go over that in a bit. But this essentially encapsulates the idea for this quantum antibody course. Okay, so this is a tentative timeline for now 2020. Everything is, of course, going to be online, but I'm going to upload at least 2 videos per week, one Tuesday and one Thursday. That's when our classes are scheduled to happen. And of course, this is already the course presentation. I'm going to do another video on a review of quantum mechanics and see what is many-body, what's many-body, what's quantum many-body, right? How do we go from, say, the hydrogen atom to a quantum many-body system? Then I'm going to go over distinguishable particles, fermions and bosons, second quantization, the non-interacting electron gas, then a tight binding model, still non-interacting, but using the second quantization formalism. Then we're going to go over mean field theories. Then we're having a break due to the September 7th week, right? In Brazil is a holiday, so no classes here, or no videos uploaded here. And then we're going to go over more formalism and talk about the representations, time ordering, Green's functions, the equations of motions. And so it's going to be 2 weeks of that. And then some models. The Anderson model, as I said, there's going to be 2 classes on Anderson model and the Condon effect. Then finite temperature formulas, imaginary time Green's functions, Feynman diagrams, momentum in both real space and momentum representation, and then we're finishing the electron gas, presenting the RPA and the dielectric response. Matsubara formalism is one class of that. Then phonons, Green's functions for phonons, and that's what's going to lead us into BCS, RPA and phonons, Cooper instability, and BCS theory. So this is the classical content up to here, and the final 4 lectures are going to be in topological insulators and superconductors. I'm going to talk about Berry phase, Hall conductance in a chair number, topological insulators, quantum spin Hall effect, and the last lecture on the Kita-F model and Majorana zero states or Majorana bound states. Okay? So, as a basic bibliography, we're going to use Bruce and Flansburg's textbook, which I find it very modern and like it very much. And of course, there's a classical text by Mahan and Fetter and Valeka that you can find in different editions. I have these two, which is I have the Dover edition. There's also an older one by McGraw-Hill from the 70s. And for the last lectures on topological insulators and topological superconductors, we can use Andrei Bernevik's book, which covers that. There's some other textbooks and reviews that you might find it interesting, but this is a book. I mean, there's a few typos in it, but I like it very much. It's very well written. So this is as far as textbooks goes. But again, I'm going to post the PDFs for the lectures on the website, so you can follow through that too, right? So grading and evaluation, this is essentially aimed for those who are enrolled in the course. So for each class, there will be at least one assignment, perhaps 2. And you typically will have a week to do these assignments and post them online at the platform. You have to log into the Moodle. And so it's pretty much every Tuesday and Thursday you have to submit something, right? And of course, these are individual assignments. Of course, group discussions on the assignments are encouraged. In fact, we'll have, besides the online lectures, we'll have a live presentation, typically by Zoom, and I'm gonna send people who are enrolled an email. We're going to discuss that a time that everybody can attend. And this, in principle, is only for people who are enrolled, but if you would like to participate, please send me an email and I can include you in a group. So this is going to be either on Thursday and Friday, and I'm going to set up a time. So that's where we're going to discuss the assignments for the week and other things. I'd like to get some feedback from you as well. And so these assignments have to be uploaded on time at the platform. Oh, and I will not accept them by email. Oh, I'm sorry, I missed the deadline and didn't post it. Sorry, that one will not be accepted. But keep, every class there will be an assignment. So the thing here to check is consistency. So the average of these assignments is going to be 7% of the grade. And there's also be a final project where you're going to choose a topic, and I'm going to go over the topics in a bit. and write an essay, 5 to 10 pages typically, and then you're going to give a Zoom presentation on this work to me and to your colleagues at the end of the semester. And that's what I posted here. These 3 weeks are reserved for your presentations for the final projects. And the topic, I'm going to have a list of suggestions, but this is very flexible. If you choose a topic you'd like to do your work on, and we can discuss it, it's fine with me. So these are some tips on the topic for both the manuscript and the oral presentation. So it doesn't have to be long. 5 to 10 pages is okay, preferably in LaTeX. Try to write not to me, but to with a structure that somebody who picks it up and doesn't know anything about the topic will learn something, right? So have an introduction with review of the basic literature, presentation in an organized and clear manner, and keep in mind, say, your fellow graduate students or non-specialists on the subject who want to just learn the basics here. That's the idea for the project. So do not write for me, write for someone else. Typically your fellow graduate students or a non-specialist. And the oral presentation, typically a 20-minute seminar plus questions. We're gonna randomly select the order for the presentation. So unless there are volunteers to go first, but other than that, we're gonna just do a random draw to see who gets allocated on each day. So here I'm gonna look at how you organize your seminar, how you control your time, and whether you have mastered the subject, and whether what's written in the manuscript matches what you were saying to us. So be clear and didactic. And seminar attendance is mandatory. So you have to be there at the required time, so that you may ask questions, and that's going to be a part of your grade, right? How often, if you did your presentation and didn't attend to anybody else's presentation, that's going to not look good on your grade. Let me just say that. Okay. All right. So that's the idea. So typical topics, strongly correlated systems. That's many possibilities there. Numerical methods in correlated systems, density matrix, randomization group, numerical randomization group, quantum Monte Carlo, etc. Here you can include matrix product states, tensor networks, things like that related to DMRG. Code atoms is also interesting, correlations. People who do electronic structure, you might want to review what is a density function theory, what are its limitations, and where you can go beyond that. So the GW method is one that treats interacting systems. I mean, in a level that is about the same as RPA or better. So this is interesting, especially if you're working in electronic structure calculations. High TC superconductors, that's a topic that's never gets old. This is in Portuguese. It should be nictites. Novel systems like magic angle, bilayer graphene, superconductivity on that, and it is a very hot topic nowadays. Topological matter, several possibilities, Majorana bound states, no topological quantum computation, via fermions, things like there are several possibilities here. Disorder, that's also an important topic that we're unfortunately not going to cover in this course, but you definitely can choose a project on this. So many-body localization, for instance, is a trendy topic nowadays. Liquids, which are also important. Probably we're not gonna have time to cover that in the course, so this is also good for a project, etc. You can come up with your own topic, and we can discuss and see if that's a good match. All right, so let me finish this video by going over that idea of more is different. And this is something I sometimes present in seminars, and I ask this question: what is fundamental, right? So for some people, fundamental are the particles of the Standard Model in physics, the latter of which, the Higgs boson, was found a few years back. This peak at 100 JeV energy. So then you have all these completed. You have the quarks here, and the leptons, and the gauge bosons for for the interactions, weak, strong, and you have the Higgs boson. Now the question is, in condensed matter, typically we have used 4 of these particles, and that's it. Up and down quarks that form the nuclei of the atoms that we have in nature. The electron is the big star in condensed matter physics, right? Sometimes you only talk about the electron. And the photon that mediates interactions between these guys and between the electrons, and we use that for probing. So pretty much these 4. And these 4 make up essentially all the materials that we have contact with. That's electrons, nuclei, and photons. And so, okay, now we say, okay, that's just 4, that's it. And then we have many phenomena that you simply cannot explain by knowing all the different properties, the energies, the rest energies, and everything from these particles. You cannot fathom when you put many of these together, what kind of phenomena you can get, like superconductivity, for instance, right? Or any phenomena in this list here. So then what's fundamental, right? We only have 4 particles. So that's what at the heart of Anderson's Moore's different paper. And he says the behavior of large and complex aggregates of elementary particles turns out is not to be understood in terms of a simple extrapolation of the properties of a few particles. So you have only these 4 particles here. What happens if you have many 10 to the 23 of them? What's the behavior there? Can you infer that behavior? And the answer is no. Why? Because at each level of complexity, entirely new properties appear. And the understanding of the new behaviors requires research, which is a thing as fundamental in nature as any other. So what's he saying here, and that's something I want you to think during the essay, is saying what's fundamental, right? And you can go to another level and say, okay, say you only are restricted to those 4 particles, nuclei and electrons. Say, let's even forget about the photon, right? 3 particles. Or quarks, up and down quarks forming protons and neutrons, and electrons. You can even forget about the neutrons because they just renormalize the mass. The question is, can you write a Hamiltonian that will describe all the matter in the universe? But let's include the neutrons here and call it a nuclear, right? And in fact, you can, right? You can just add the kinetic energy of the electrons, kinetic energy of the nuclei, a sum that runs through all the electrons in the universe, and all the nuclei in the universe. And then you include interaction, so the photon is in there, hidden somewhere, but you have repulsive interaction between electrons, repulsive interaction between the nuclei, and an attractive interaction between electrons and nuclei. All right. So that's your Hamiltonian, right? If you know, what's not in there? Nuclear forces, gravity, but for the properties of the everyday matter, this is all you need, right? So it's all in there. If you can solve this equation with this, you could in principle explain everything, right? That's the theory of everything. And this is an interesting paper by Bob, as I said, by Bob Laughlin and David Pines in 2000. Now the question is, can you solve that? And the answer is no. And even if you can, the theory of everything does not predict everything, right? So yes, you can solve that for small systems, typically of order 10 electrons and 10 nuclei, and that's it, right? The complexity for solving these equations grows exponentially with the number of particles, right? So an exact solution is only available for very small number of particles. Then you can do approximations, right? So large systems are much harder problems than the quantum many-body problem. That that's what we're talking about. And then you can say, okay, all right, I'm not going to solve this exactly, but I'll do some approximations. Say, for instance, I'll say that the nuclei are at rest. They're much heavier, so this mass term is much larger than this one, and I'm gonna just treat them as if they were frozen in space. So I get rid of this term, and then this will just become a one-body potential. So it simplifies for the electrons, say. And then they are fixed, so this is just a constant, doesn't matter. So I simplify my problem, right? But still, it's still a hard problem if you have many electrons. So you can definitely do these approximations, and they work well in some regimes like Hartree-Fock, DFT, and with these approximations that are intrinsic to the model. And then you can try to solve some version of this equation for the problem at hand. But even these approximations, they will not solve every problem. Some problems, they do give answers, and you can definitely compare those results with experiments, but it's not always. Now, for some problems such as this one, the conductance quantum and a quantum Hall effect, or the quantum magnetic flux in superconducting rings, Josephson effect, for instance, as well, vortices, magnetic field generated by rotating superconductors, things that involve superconductivity, for instance, which is a many-body phenomenon, and is a collective phenomenon, are not well described by these equations. And all these topics here, they are really, really important, of fundamental importance. Why? Because the experimental measurements of some of the fundamental physics constants rely on this. Like the standard for E squared over H comes from the measurement of conductance in the quantum Hall plateaus, right? And you simply cannot get the quantum Hall effect out of something like that. And why is that? Why you can solve it, and you cannot see the quantum Hall effect happening here? Well, because these are all emergent phenomena, and in that sense, this gives you too much information and at scales of energy which are far different than the ones that you were really interested on, which is the energy scales where these things become relevant. And these things, they emerge and they become the dominant phenomena at that regime. So the theory of everything cannot predict everything. That's one thing that I like to, that's why we do what we do in this course. We do quantum antibody theory for some, you can call them simplified models, but they still capture the main point of the physics behind the problem at hand. So just to summarize this paper, the Laughlin-Pines paper, they say we have succeeded in reducing all the ordinary physical behavior to a simple, correct theory of everything, only to discover that has revealed exactly nothing about many things of great importance. And so this is what I call the more is different paradigm. And the first assignment, which is due now in 2020, due on August 25th, which is a Tuesday, so you have to upload that to the Moodle platform, is to write an essay. Read these two papers and write an essay of what you think of them, right? So both papers are already available at the Moodle website. And you know what we expect that this is. I'd like to read what you have to, how you write, how you present your ideas. You don't have to agree with me, right, with everything I just said. You might say, okay, well, no, I have a different view of that, and I like to see it in your presentation. Why? Writing skills and communication in general is very, very, very important in physics. If you want to follow a career of research in physics and many other areas, communication skills are really important. But writing skills and writing in a clear way is really very important. And sometimes they are not emphasized well enough in physics courses, either at undergrad level or at graduate level. Sometimes we're just too focused on solving problems and getting, correct answers, correct, quote unquote, so to speak, that we do not pay much attention to how you present them and how you try to convince other people that those are the correct answers, right? Also, I'd like this to be a sort of a critical reading of the papers. So not just, summarize them. I'd like to see your opinion on them, right? Based on some consistent argument. You don't have to write a book, 2 or 3 pages should be fine. I would strongly suggest that you write it in English, but if you want to write in Portuguese, it's fine. But English is the lingua franca in English, in physics, I mean. And so it's a good exercise if you want to try to push yourself to write this in English. But you can write in Portuguese as well. So you might upload a PDF on the Moodle platform by Tuesday at the end of the day, 11:55 p.m. So this is the first presentation, and I'll see you in the next video, and let's start the course. See you in the next video.